I'm Anil Kumar. Welcome to my series on probability. In this video, we'll discuss the cases which are under the category dependent and conditional. In previous video, we understood few concepts about probability and took some basic questions to get started. Now here it is more difficult questions where we'll look into dependent and conditional probability cases. As we dealt with this earlier with simple examples, we'll begin with where we left, knowing fully well that probability of B, the event B, when A has occurred is given by the formula probability of A and B divided by the probability of A, correct? Now this particular formula can also be written in the product form, and this is also called rule of product. So you can just kind of cross multiply and write down that the probability of A and B is probability of A times probability of B when A has happened, when A has occurred, right? So that is what it is. So you'll notice that this formula is slightly different from the formula which you see. So you notice that this formula is slightly different from the formula which you have seen for independent cases, correct? So I hope you remember when we're talking about independent cases, what was the formula? Okay, so I hope you remember. So probability of A intersection B, let me write probability. Okay, so probability of A intersection B is the product of these two, right? Product of probability of A times probability of B. However, in this, when you have a dependent case, the formula changes. And what happens really is when we say probability of A, I'm writing it in a different way than it was written there, when B has occurred is equal to probability of A intersection B. Remember, A intersection B and B intersection A is one and the same thing, right? And in the denominator, you get probability of B when you're looking into what has happened already, correct? That goes in the denominator. So that becomes your sample space. So think about it like this, that this is the sample space for you, right? So when you're talking about the conditional probability, probability of what has happened is your new sample space. And now within that sample space, we are looking into the probability of what is going to happen for a new event, which is dependent on that event. So I hope this concept is absolutely clear. Okay, so now let's see what is written here. Two or more events that occur in a sequence are dependent if the outcome of any event changes the possible outcome of the other events. So it could be either way, right? Probability of B can affect probability of A, probability of A can affect probability of B. Now in this sequence events, you could consider either way. Do you understand the idea, right? So we'll have examples which will further clear this particular point. Now, before we get on to the real examples on this, let us understand the concept, the relation between dependent and independent events, right? So, as you know, if the event is independent, in that case, the probability of A and B is the product of probability of A and B, correct? Now, when it is dependent, we have a different formula. But in the numerator, you do have an expression which is probability of A and B. You can replace this with product of A and B when it is a case of independent event. And when you do that, then probability of A cancel. And what you get here is that the probability of B when A has happened is actually equal to probability of B in case of independent event. Do you see that? So it is the same probability. However, remember that if it is a dependent event, in that case, it is never same. So that is another way of proving algebraically whether the given information relates to dependent events or independent events. Perfect. So I hope you find it very useful, right? So here I've summarized this for you. For independent event, probability of B when A has occurred is equal to probability of B. But for dependent events, probability of B when A has occurred is never equal to probability of B. Correct? It changes. Now, whenever we are using this term, probability of B when A has occurred, it is to be read as probability of B when A has occurred. Now, this bar which you see in between is condition, right? So that gives you the condition as generally we use in mathematics, correct? So condition is that A has happened, right? This we need to find, and this happened. Correct. Now with that, let's take up some examples. So example number 1 here is 6 green marbles and 4 red marbles are placed in a container. The marbles are identical except for the color. 2 marbles are selected at random in a sequence without replacement. What is the probability that 2 red marbles are selected? Now, this example we are going to do in 3 different ways so that you get fairly good idea of what are we trying to do. So we are having 6 green marbles. Let me just sketch 6 green marbles here. Let's say these are our 6 green marbles. And 4 red marbles. So let's have 4 red marbles. Now these are in a container we're talking about, correct? So these are in a container. Now, the marbles are identical except for the color. As you have seen, 2 marbles are selected at random. So we are going to select 2 marbles at random in sequence without replacement. So once you select one, the number of marbles decrease. Perfect. What is the probability that 2 red marbles are selected? So first red, then the red numbers will decrease, correct? And then the second red. Okay, so let's define our events. Let A be the event that the first marble is red, right? So for this particular event, first marble is red, we have 4 red marbles, total is 10. Probability of choosing a red marble in the first trial is 4 out of 10. Perfect. Now let the event B be even that the second marble is red. So B's second marble is red. We are not putting a condition there. Second marble is red. That is what we are saying. Now, let's look into the question itself. Now, first, we need to find 2 red marbles, right? So sequentially, we're looking for red followed by red. That is what we are interested in. Now, to solve this question, we are going to use 3 methods. Method number 1, we are going to use the product rule, right? Product rule is, let's get back and see what the product rule was. Whenever we have dependent conditional cases, then the product is probability of A times probability of B when A has occurred, correct? So we'll use this probability of A times probability of B when A has occurred as the probability of A and B. Since we want both red, right? Event A is red, B is second time red. Perfect. Now what is the probability of A? Well, 4 out of 10. Now once you select one of them, it goes, we are left with 9 marbles and 3 red marbles. So 3 out of 9 is probability of B when A has occurred. So when A has occurred, 1 less red marble and 1 less total number of marbles. When we do the product of these two, we get 2 out of 15 as A intersection B. So we get our result, which is 2 out of 15. So that is the answer. So we get our result as the probability of 2 reds is equal to 2 out of 15. Now let's apply the second method, which we'll look into, where we are using the formula directly. That is to say, we want the second to be red when we know that the first one is red. So probability of B when it is A has happened. That is, we have already selected a red marble. Now what is the probability of getting a red marble? So the formula is the probability of intersection of A and B over probability of A. Now, we know that the probability of B when A has occurred will be what? If A has occurred, we have already taken away one marble, right? It was without replacement. So, we have 3 left red marbles out of 9. So, this probability is given to us as 3 out of 9. We know what is the probability of A. It is 4 out of 10, right? Now, from here we can rearrange and find probability of intersection of A and B, right? Writing B and A intersection and A and B same thing. That is 2 red marbles. Is cross multiply, get your result, which comes out to be 215. So 2 over 15 is our answer. So either way you do it, you get the same answer. Now, let's look into the tree diagram to solve the same question. So let's begin with our container, right? So we have a container here in which we have all these marbles, right? So we have 6 of these green marbles and we do have 4 red marbles. Now, in the first selection, what is the probability of getting a red? Of course, it is 4 out of 10. So we get 4 out of 10 here. Once a red is selected, we are left with 3 red, 9 others total, right? So now the probability is 3 out of 9. So the probability of A and B to happen is the product of these two, which is 2 out of 15. So tree diagrams are very easy and effective ways of solving these questions, especially if there are less than 3 layers, you can say. Okay, so that is how you could do with the tree diagram. It also gives you an idea of other kinds of questions which could be asked on the same information. Now that is important when you are learning probability. Now let's move on to the next type of example. The question here, example 2, is students in a class appeared in 2 tests. 48% of the class passed in the first test and 30% of the class passed in both the tests. What percent of those who passed the first test also passed the second test? So conditional probability, those who passed the first one also cleared the second one. That is what it is. So let's define our event. Event A, students passed in the first test. Event B, student passed the second test. Conditional probability, we want to know what is the probability of students who passed the second test when we know that they already passed the first test, right? That becomes the conditional probability. So it is the intersection of A and B divided by the probability of A. We are already given that the probability of intersection is those who passed first and second is 30%, so which is 0.30. And those who passed the first test is 48%, written as 0.48. When you divide, you get 0.625, right? So that becomes your result. Now, in this particular case, we were given this information which has been applied here to get the solution. So I hope this concept is absolutely clear. So percent of those who passed the first test also passed the second test is 62.5%. Clear? Example 3. Now, the probability that a train departs on time is PD 0.82 and the probability that it arrives on time is PA 0.9. The probability that it arrives and departs on time, that is intersection of these two, is 0.75. Determine the probability that a train, so now we have 3 different conditions to work on. Let us see these conditions one by one. Arrives on time given that it departed on time. So first condition, we are assuming that it departed on time. That has happened. And now we want to figure out that what is the probability that it arrives on time also, right? So probability of A when departure was at the correct time will be intersection of A and D divided by the probability of D. Intersection of A and D is given to us as 0.75. And we are going to divide that by probability of departure, which is 0.82. Once you do that, you get your answer, which is 0.915. Is that clear to you? So that is how this formula is very handy. And I hope you have got this formula now. B. Departs on time given that it arrived on time, right? So probability of D when it is known that it arrived on time. So intersection of D and A divided by probability of A. Now these figures are also given to us. When I divide one by the other, we get 0.833 as our answer. C is very interesting. Are the events of arriving on time and departure on time independent? That's the question. How will you answer this question? Are the events of arriving on time and departure on time independent? Think about it. Well, we understand that independent events, probability of A and B happening, is product of their probabilities. So let's check probability of arrival times probability of departure. Do we get probability of A and D? Let's check it out. So when I multiply probability of A with probability of D, which are given to us as 0.90 times 0.82, we get 0.738. However, it is given to us, it is 0.75, not 0.738. And therefore, it is a dependent event. It is not an independent event, right? So we can conclude the probability of A intersection D is 0.75, which is not equal to 0.738, and so the event is dependent, correct? So the event is dependent. Example 4. Now at this stage, I'm going to share with you some interesting strategies. So see, strategies for quick solution. How do we get quick solution with minimal calculation, especially for a multiple choice test paper? Let's see that now. Example 4. A couple has two children. Find the probability that both are boys if, so we want both to be boys, right? So we want B1 to be boy, second one also to be boy. Both to be boys when some conditions are given to us. Condition number 1 is one of the child is a boy, right? First is a boy, second is a boy. One of the child is a boy. So that is the condition. Okay. Now, what we could do here is arrange the data in the tabular form, like a matrix. So let's say B1 is the first boy and G1 is the first girl. So initially, there is a possibility of having a boy or a girl. In the second time also, there is a possibility of having a boy or a girl. Their combinations are given here in the table, right? Now, when we say one of the children is boy, then out of these, you have only three possibilities, right? Out of which we are looking for one where both are boys. Do you see that? So out of three, only one is both of boys, and therefore, if one of the children is a boy, we don't know which one. If one of the children is a boy, then the probability is 1/3 of two boys. You get the idea. Now, let's look into the second case where the elder one is a boy. We know the first child is the elder one is a boy. So we are now restricting ourselves to this particular group where the first one is a boy. Out of these two cases, only one is a case where both are boys. So the probability now is 1/2. Do you see that? So it is different in two cases, and that is how very easily with the help of this table you can get the answer. So when there are multiple choices, you can actually make a matrix like this and solve. So tree diagram and these matrix tables are very helpful. And here is another strategy. Well, let's talk about cards now. Here is example number 5. A card is drawn from a deck of 52. Determine the probability it is a queen given that it is a face card, right? So that's the question. Now, we'll define our events as Q for draw a queen. What is the probability of drawing a queen? There are 4 queens out of 52 cards, so the probability is 1/13. 4 over 52 reduces to 1 over 13. Event of getting a face card. There are 12 face cards, right? So F is our event for face card, probability being 12 divided by 52, which is 3 over 13. Now, in this case, it is important to understand how do we get probability of intersection of queen and the face card. Well, you can see all the queens are face cards and therefore their intersection is same as the probability of getting a queen itself. And this intersection is therefore 1 over 3. So the probability of getting queen and a face card is also 1 over 3. Now, let's use the conditional probability to find the probability of queen given that it is a face card. So now probability of given queen given that it's a face card will be intersection of queen and face card divided by the probability of face card. So we have 1 over 13 in the numerator, 3 over 13 in the denominator, which simplifies to 1 over 3. So that becomes our answer. Perfect. Now, let's look into an alternate method to solve this particular question. We know that there are 4 queens and there are 12 face cards, correct? When we know that the card is a face card, then that becomes the total number of possible outcomes. Out of them, 4 are favorable and therefore 4 over 12 or 1 over 3 is the probability of getting a queen when it is known that a face card has been drawn. Does make sense to you? Perfect. So if an event has occurred, then the domain is restricted and so the probability can be calculated treating that as a sample space. You get the idea. So the probability that it is a queen given that it's a face card is 1 over 3. Got it, correct? Now let's see how we can apply it in different cases. Same strategy. We are going to apply now in example 6. A die is rolled twice. Find the probability that the sum of the two rolls is greater than 9 given that the first roll is 5, right? So we're looking for sum greater than 9. So we'll define two events. Event A is that the first roll is 5. Event B, sum is greater than 9, correct? So we need to find probability of event B when it is known that event A has occurred. That means in the first try you got 5, correct? Now let's look into this. Getting a 5, the probability is 1 out of 6. There is 5 out of 6 choices. Now, possible outcomes for A and B are what? If you get 5, how do we get more than 9? That is only possible if the second trial you get 5 or you get 6. So these are the two possibilities and therefore the intersection of A and B is 2 over 36, which could be written as 1 over 18. So now we know the intersection of A and B. We already know the probability of A, that is rolling a 5, which is 1 over 6. So dividing 1 over 18 by 1 over 6, we get the result 1 over 3. Is that clear to you? So the probability that the sum of the two rolls is greater than 9, given that the first roll is 5, is 1 over 3. Correct? Now, let's look into the alternate method where we will redefine a sample space. We know that the first row is 5. You get the idea, right? So that is our first row. So we know it is 5. Do you see that? So we have, these are the two dice. Twice we are throwing it. First is out of which we are looking for number greater than 9 when you add it up, right? So there are only two ways to get it. Out of, we have here 6 possibilities. So therefore, 2 out of 6 or 1 out of 3 is your answer. So restricting the domain and then working out is an extremely good policy to do conditional probability questions, especially when we have dependent and conditional probability cases. I hope that makes sense. So with that, we come to an end of our video. We have learned a lot. You can always contact me on the email address given here. Feel free to write your comment, share your views, and if you like and subscribe to my videos, that'd be great. Thanks for your time and all the best.